All right, so okay, well, hope you get a little bit of a break, so from now on we can go for another 4 hours, I guess. Nobody's scared of that, okay. All right, so the second portion would be, well, so as you see what I tried to do the first hour to give you physics background of entanglement and what it is, how to take the mystery out of that and to understand the physics of it. And again, after you understand the physics, it's a common for every area you would ever work into. First, you take the effect, you study it. After you study this effect, you start to understand it. You kind of dissect it in pieces, put it all together, make a nice theory, it's all working together. Now you have knowledge of that, right? And after that, you can use it. You can start using it. And the first thing in terms of entanglement started that I learned personally after kind of demystifying it for myself as an experimentalist. By the way, being experimentalists helped a lot to demystify this because every time you make entangled state by hand, deliver it to the detectors, measure them, bring signals together and measure Bell's inequality. And when someone starts telling you about non-locality, you're just looking there and asking, where is the non-locality? Local, 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 local. Okay, I take my detectors, I put it, I don't know, 100 kilometers away, 200 kilometers away, 1,000 kilometers away. What changes? This air, in the best case, usually like in theory, is vacuum between these places. It doesn't change anything. So that's really helped to understand, for myself personally, that there is no any problem with quantum mechanics. And by the way, later on I learned that this Einstein-Podolsky-Rosen paper was not just one single case of confusion of big people. At that time, actually it's another very important thing. You know, I've seen this, like people were, you talk to someone about some fact, they say, well, that's obvious. Well, it's obvious now, but like when you started this 20 years ago, it was not obvious at all. Nobody knew at that time what it was. The same with entanglement. When Einstein, Podolsky-Rosen argued with David Bohm about the completeness of quantum mechanics, nobody knew what it is. It was just a really new theory at that time. By the way, do you know that Niels Bohr, published a reply 3 months later under the same title. The EPR paper went in May, his paper went in September. Raise your hands who knew about the second paper. Yeah, that's what I thought. I did the search, so how many times the EPR paper cited and how many times the Bohr's reply cited. The ratio is really like this. So, because at that time they were arguing multiple times, if you're interested in the history of quantum mechanics, you can read the Wheeler and Zurich book that has translation of recollections about the Solvay congresses from 29, 30, 31, 32. That's where the formation of quantum mechanics was happening, and Einstein, and Schrödinger, Pauli, all of these people, they were sitting at the dining table, basically for breakfast, lunch, and dinner. And someone brings the question in the breakfast, and then, like Einstein will pose the question in the breakfast, and Bohr will answer during the dinner, for example. And that question that we discussed today was of the isolated quantum system was a key point that was going again and again and again from that discussion. Read it, because, for example, the example that in that book was used is Einstein was confused about what happens with the electrons going through double slit. Basically, electrons, real particles, go through a double slit. how to, what's the difference between electrons going through and waves going through, and how to describe, how quantum mechanics can describe the interference, and so on. And basically, then it boils down to momentum conservation. And Bohr, like in the next meal, was answering to him, saying, oh, but when the electron goes through the double slit, it gives the momentum to the slit, because it deflects, right? The deflection means the momentum goes there. But the momentum goes to the slit. Slit is bolted to the table. It's now part of your system. You have to include the slit and the table together, and that's your isolated quantum system. Now you apply quantum mechanical conservation, you will get your result. Because the impact on the electron is proportional to the back action of the slit, and the back action of the slit is rationed by the masses, but not only of the slit, but also of the table that is bolted to. So that's a kind of, you can see that this type of problems of considering isolated quantum system were going back and forth at that time. All right, after we learn all these things, basically we can start using them. And as I told you in the lab, you evaluate Bell's inequality, you try to make them as good as possible. This is the kind of stuff. And as good as possible, then you want to have as many as possible, because it's a statistical process, it's probabilistic, right? Alan Aspey was waiting for hours to get enough statistics, so almost days to get this thing. So with down conversion, originally, we were not hours, days, but kind of minutes, tens of the minutes, and so on. And we were trying to get more and more and more to increase the number, so to minimize the observation time. Although, and we'll talk more about this, we have to be careful. So the one important thing for all quantum information, all quantum physics, quantum experiments is, again, you have a source, propagation, and detection. So you have to make sure that none of this spoils your quality of the state until you detect it. Okay? So then the question is, how many of these states you can create? So your process creates them, either particles or photons as a quasi-particle spits out and it goes out. But every photon, for example, is a wave, right? It's a wave packet, actually. So it has a spectrum, has a time. So the main thing is, in all quantum systems, so you create a quantum system, it propagates. You don't want it to overlap or mix with anything else. So the minute it starts mixing, it's a mixed state, it's classical physics. Okay? So it has to be kind of well separated. So you can count for any source quantum dots, atomic down conversion, whatever else you have, atoms, how many per second you can have them. Just make sure a majority of those sources are random, Poisson. So you have to make sure they do not overlap. The minute they overlap, you're out of the quantum domain. Now, when you propagate them in space, very often there is dispersion in space. Dispersion like broadens the wave packet, they start to overlap. Again, you're out of luck, you're in the classical domain. If you lose them, well, you have to wait until the next one. So you just, actually, that's the easiest part. You just only pay the time, price of the time. Okay, and then detection, you have to detect them as good as possible, with highest possible efficiency without mixing them up. Okay, so, well, this will go quickly because we just went through this. Now, sources of quantum correlation photons and design of photonic superposition. Remember, entanglement is correlation and superposition. If I have correlation and if I know how to make superposition, I'm a quantum engineer, quantum entanglement engineer. And I'll show you also the role of sources and role of detectors. In fact, even though detectors are classical devices, it's a boundary from quantum. What they detect, what kind of information they deliver to you matters. Actually, what matters is what they do not deliver to you. If they don't give you information about something, and you don't see that flow of energy your way, it doesn't exist for you as an observer. And it happens to be another tool for engineering entanglement. Now we'll talk about this. Okay, so we've seen this already. Again, entanglement could be classical, could be quantum. When people use originally the word entanglement, it was mainly related to the quantum, but in the classical domain, classical entanglement is nothing else than the coherence theory, especially when you go to the electromagnetic waves. Take Born and Wolf, it's all described there. And then also the Mendel-Wolf. There is a second thick, there are two thick books. Emil Wolf and Max Born, and the Emil Wolf and then Mendel. There are two books that everything is in there. But with Mendel, there is lots of quantum there as well, but classical is described as well. Because in principle, classical correlation or coherence theory is extremely well developed. In fact, Roy Glauber was why he got his Nobel Prize, really. He was one who kind of showed the formality of transition from here to here. He really showed how to translate from one domain to another, what rules you have to obey, and how it's going. That was his major contribution. All right, so now, again, superposition and correlation. With photons, as I said, photons are excitations of electromagnetic field. In fact, it's, well, since it's a school, so let me just talk just 5 minutes about the photons. Now, who knows what the photon is? Yeah. Click in the detector. That's good. That's good. But why people say, okay, the photon goes here, it goes to the beam splitter, one can go to the left, can go to the right. It's still before the detector, and they're still talking about the photon as a particle, right? So it's. I got lucky in my life. Around '93, I participated in a nice 3-day seminar by Willis Lamb. You know, he got his Nobel Prize for Lamship, but he, at the end of his, he also was one of the major contributors to the theory of laser, Lamb's color model. And we were interested in quantum optics. We had a discussion and showed them what we were doing. And he said, well, actually, strictly speaking, it makes no sense to talk what you're talking about. And he explained. So let's do formal mathematical and physical thing, how by textbook. So you have a system. You have laser, nonlinear crystal, you have beam splitters, mirrors, everything, and then detectors, right? So all until detectors, it's a linear optic. After the laser, or I said, after the nonlinear crystal, and until the detector. All these things is linear optics, unitary transformations, right? So what it is, it's a distribution of electromagnetic field. How you describe it? There are wave equation and boundary conditions, right? You can take this, throw it inside the computer, solve it for normal solutions. You have normal modes of that system. Classical problem, right? Now, this is, by the way, remember this distribution of electromagnetic field in space is a classical problem because it has some relation to quantum imaging, which has classical and quantum parts to it. Now, when this becomes quantum, and like when quantumness comes into the electromagnetic, it comes at the stage of the secondary quantization. What is the secondary quantization? About creation, annihilation, operator. What they do? They do nothing to the mode. They change the energy inside that mode, right? That's what it is. That's where the quantum is coming. When it comes to the energy populating those modes. Okay, fine. So you solve the problem of your experiment. Now you could say, okay, in this mode there is energy h omega, energy of omega, but it belongs to the whole mode. what is the main definition of the mode? Well, the nearest one will be, think about the laser mode. It's the simplest one because it's one straight line, right? When you have a laser mode, you don't know where your photon is inside, right? It's a self-coherent. The single mode is self-coherent entity. Everything is coherent. What is the coherence? Means a stable phase relationship, but the second expression of that is indistinguishability, where it is, right? So you don't know, that's what it is. So it's an excitation of the photon somewhere inside the mode that is defined by the structure of the optical system. He even wrote a paper. It's called the anti-photon. Check it out. It's a physics letters in '94, I believe. Willis Lamb, 1994, Physics Letters A journal. Big journals didn't want to publish it, even though he was a Nobel Prize winner. So, and the paper is called anti-photon. Anyway, so that's just about the photons to be quantum particles. They are not solid particles. And this is important because they interact with many, just remember this, for engineering this is important. But photons have different parameters. What parameters we can use? Well, spin is spin, it's particles. Photons, well, the polarization is the nearest to the spin. It's the easiest one, right? But then, in addition to that, you can have phase, I omega t, right? Well, the phase has two parameters, I omega t and kx, right? So there are two contributions. You can really use this as two different parameters. The direction k is a direction in space, even though it's classical, but phase is another parameter. And you can use, as I said, parametric down conversion. So again, nonlinear crystal has to be nonlinear to move energy between different modes. By the way, this is just side note on quantum information processing. You may have seen that the frequency sometimes has been used as a variable for quantum information processing. So you can encode qubit also. One frequency is 0, another frequency is 1. Usually there is a big problem with those types of manipulations of qubits. Remember, qubits, you should have the superposition of qubits. And superposition of two frequencies means another frequency. So you cannot do this without nonlinear interaction in physics. So, and nonlinear interaction doesn't go into quantum mechanics very well. You have some trouble on the side. So you have to deal with that. But polarization is okay, phase is okay, they're both linear parameters. And that's what people use. So they give you correlated source. And this is conservation of energy. This tells you that basically this could go anywhere in between here. The combination of those frequencies could be different. The K-vectors are important in optics because K-vectors are associated with modes, right? Remember what's the definition of K-vector? What is the definition of K-vector? It's a normal to the wavefront of the plane wave, right? So if you have something in there, that's already another wave, right? So if you have only one, that's one. When you have many, that's a spectrum. There's a spread. Okay, I've shown you this one. So this is type 1. Type 1 means here's the laser gun here, and then they're going out, and they all of the same color. Let's just, since we cannot do experiments, let's just try to see the impression of the experiment. Actually, can we just take those slides off again? I think they came back because the contrast is not so good. It's not so bright here, so let me see if we can run it again. So the type 1 down conversion. So we have laser here, nonlinear crystal, and then the photons go in pairs. They always go on the opposite side from the laser. laser, and the colors are matching together. The energy of this two will be energy of that. So it's a correlation in time. They always come together. Correlation in momentum on the opposite sides, and but the orientation is the same of polarization. If you increase the power of the laser, there will be many more of them coming, but watch out, because if they start to overlap, it's not good anymore. So, so that's type 1. That was not so important. All right, type 1 down conversion. So it's a source of correlated photons. Just to tell you that even that is already interesting and important for a number of applications, including the metrology. How is it interesting? So if you have a source of photons, so one photon goes here, another photon goes there. So if you have, this is one photon detector, and the joint energy is energy of this pump. It could happen, if this is ultraviolet and this is green, that could be red or even infrared photon. And it's very easy to detect the green photons, silicon avalanche photodiode, doing very well. But imagine that this photon is around like 1, 2, 3 microns. How to make sure, because what the metrology is. Metrology is, you know what's coming to your device, and you measure the response of the device. You have to know, like, one photon comes in, what do I have? Or like 2 photons coming, what do I have? The response of the thing. So, but how would you know that it's really what one photon comes, and then another one at which particular time? Nature doesn't give you this source. The best source metrologists usually have, it's a black body radiation. But it's, there's a distribution there, right? So laser is Poisson, black body. Well, if you go to very low intensities, it's also basically Poisson. Well, what we can do, we can think about the source. So this is the laser, this is the detector, this is the crystal, nonlinear crystal. So from time to time, it gives you 2 photons. Then this one, this detector, one of the photons is detected by this detector, and it gives the electrical signal to this mirror that opens up and allows another photon, twin brother, go through, and then it closes back. Just let me show you once again how it works. Okay, so you see this, just this pulse doesn't create anything. This creates 2 photons. This one is reflected, but this detector opens the gate. Sorry, this detector opens the gate and it's coming here, and then gate is closed. So if you do this, if your gate has nanosecond scale, you know within this 1 nanosecond there is definitely 1 photon was going there. And for a number of devices, it's imagine, you may have seen people saying, oh, we have a night vision device that is so great, it is sensitive to like 2 photons. Another person will say to 3 photons, to 5 photons. When you hear something like that, you mean they have no idea how many it is in reality. Because what they can do, they can only do like 3 plus minus square root of 3, or 2 plus minus square root of 2. It's distribution. Here, you can say, okay, within, let's say, 1 microsecond, I can measure how many photons you will send. And the sensitivity, time sensitivity of infrared detectors is usually milliseconds. So for them, it's instantaneous. You can say, okay, I have a device, and within 1 microsecond, I can send 5 photons. Let's see, do you have a visual on the screen of the device or not? Then, if it is, let's reduce 4 photons. 3 photons, 2 photons. So basically, it already gives you the something that is called the absolute photon source. While these days, this also has the name of heralded source. This term, heralded, appears probably like 15 years after we used the absolute photon for that. And actually, that's what I was doing in 1980 when Alan Asper was doing Bell's inequality violation. I was doing this with down conversion. He did this with atomic cascade decay. You can also measure quantum efficiency of detectors without any references. It's a big problem in metrology, how to measure efficiency, and that's exactly what we just discussed. So if you don't know how many come, so the reaction will also spread. But here, if you know that 5 photons came in, and you have only 3 responses, it's efficiency of the detector, 3 out of 5, right? That's what it is. Basically, that's the whole principle of quantum efficiency measurement. All right, now we go into the type 2 down conversion, and as I discussed, this was the, we did lots of type 2 down conversion around 92, 93, and then in 94, when Anton Zahlinger moved to Innsbruck, they asked me to come over to put together the type 2 entanglement demonstration. At that time, I attended the first European clear. The first European clear was in 1994 in Amsterdam. So I attended that conference and flew to Innsbruck, and that was our result of our efforts. What is this? Is that. Let me just do this. Also, we try to see what happens if we have enough contrast on this one. Yeah, so introduction. So here's a laser, nonlinear crystal, and we put it in such that way that this is all depolarized vertically, this is all horizontally polarized. You see different colors are available, and photons are coming with these polarizations attached, all vertical here, horizontal there. They always come with momentum conservation, meaning they both always on the opposite side relative to the pump. Here, and there are colors, this and that, and together give you energy of the mother photons. So correlation in time, correlation in momentum, correlation in polarization, correlation in energy, correlation in everything. And as we discussed, the only thing is missing is superposition. So what we do, at some point when we're tired of looking at this picture, we stop and we tilt our crystal. And you tilt crystal, you change phase measuring conditions, and you can discover this situation. And in this situation, as I mentioned, these two areas are indistinguishable in terms of colors, in terms of the K-vectors, in terms of energy color, the K-vectors. You cut them out. You put pinholes, one pinhole here, one pinhole there. Okay, now you have two beams. Same color, same distance from the center, but now you don't know which one is which. And that's what happens. That's right here you have generated entangled state in polarization. Indistinguishability, complete superposition in all parameters, including polarization. HV or VH, you don't know which one. Okay, so now we can move into the detection of these effects. Okay, let's put one polarizer at 45 degrees in one of the arms. Because it's 45, but it's EHOV, so basically 50% of time it goes through and 50% of time it does not. It's a rule of polarization filtering, right? So it's 50 cosine square law. But then you put the second one, you put two detectors and coincidence circle. This is at 45, this is at 45, you keep watching, and what happens? You start to notice that sometimes one photon goes through, but the other one not. There is no really coincidences happening at all when the polarizers are at the same angle. Now, what we'll do, we'll swap it. We'll change one of the angles by 90 degrees. Now at 45 minus 45. Well, now what happens is either both go and give you coincidences, or both doesn't go and no coincidences. Either or. And basically 100% of detection efficiency, statistically of course. And so let me stop it here. So what you can do after that, so you can do the mapping. So on the horizontal axis, it's an angle of your analyzer. On the vertical axis, it's how many coincidences per second you will have, rate of coincidences. And you keep tracking this, just by rotating this. And what you would see? You would see the cosine square curve as predicted by quantum mechanics for any vectors and the projection of the vector, either spin or polarization is the same. And if you have a 100% visibility here, when if your state before this detection apparatus is pure entangled in polarization, your visibility here will be 100%. It's a simple math. That's basically, if out of this curve you pick up 22.5 and 67.5, 135, 132.5 and so on, these specific numbers, you'll get the Bell's inequality violation. Okay? The visibility is your indication of how clean the state you have here and how good Bell's inequality violation you would have. And that's exactly what every student in my lab doing hundreds and hundreds of times during their PhD from the beginning. And after that, basically, you could see, like, you want Bell's inequality violation? No problem. Or you want to have this, the other thing is, when we started to do this for quantum cryptography applications, so what we did, we keep one detector with you at the Alice and take the other one to the Bob, and we'll have a next lecture, tomorrow, a whole lecture on that. And you can move it pretty far away. Nothing changed, basically. It still will be exactly the same thing. Sorry, oops. Let me see. Yeah, let's continue. So basically, as you can see, if we're moving it back 100%, basically that's how any experiment with down converging look like. It's almost like you've been in the lab and watched it. So, except that it was the impression of Alex Roth, one of my colleagues who did this animation. One more thing I wanted to point out. Remember I told you entanglement in phase, in polarization. There is also another thing, it's called entanglement in frequency. What the entanglement in frequency is about, so this is signal, this is idle. Spectrum. The size of this, well, it's approximately, it's really sine x, or sinc function, sine x over x, this distribution. It's just simple nonlinear optics. Basically, the interference in the length of the crystal, that's what it would be. Traditionally, in classical nonlinear optics, basically everything here is correlated with everything there. That's all. With down conversion, with this, when your pump is delta function, we have an internal substructure in there. So if you here move a little bit plus delta from the center of the wave packet, then you can correlate it with something minus delta on the other side, and vice versa. And this is distinguishable because the uncertainty of this correlation is substantially smaller than the width of this wave packet. So basically you can have red, green, plus minus green, red. This is another entangled state, omega. So you cannot use it, I told you, for superposition, it's not good. But you can take the advantage of the symmetry of the states available for a very interesting effect. It's called the dispersion cancellation effect in quantum optics. All right. So how to generate entangled states? Engineer that. So first of all, we started with the state VHHV, or HVBH, as we discussed. It's called the psi plus state. Well, how to generate different state, phi plus? Very simple. You just put the half-wave plate in one of the arms, like in signal. Then V becomes H becomes V, and you have HHVV. Linear optics, basically. Well, how to change the sign between them? Very simple. You just have to introduce some kind of phase between these two options, and it's a phase. Phase could be dynamic, like space position, for example, or basically just any kind of differences between H and V. That could be piece of birefringent material, for example, in one of the arms, something like that. So basically that's what you can do. You can go between all four by using simple linear optical combinations. Okay, as I said, so we have type 1, correlated states, type 2 allows you to do superposition. That was the beginning of the story. Long story that is now almost 30 years long. Like you have it what you have it. And you try to maximize this type of states to make crystals better and so on and so on. And then we ask the question, the first attempt to engineer entangled states was thanks to Paul Kwiat. He said, okay, instead of finding this type 2 crystal with particular directions where this phase matching is satisfied, can we do it more simple way? Take two type 1 crystals. Remember, type 1, this one gives you 2 photons horizontally, vertically polarized, and if you rotate the optical axis, it will be 2 oriented this way. Can we just sandwich them? And sandwich them in such a way that they will be indistinguishable. So try to make, well, originally to make them indistinguishable, you have to make them really, really very thin crystals. It's like 2 cones, but one is V polarized, another H polarized, so you will have this state. And again, by placing right here phase plates, half phase plate or phase shifter, you can go to any other belt state as well. So first step towards the engineering entangled state is instead of type 2 crystal, use 2 type 1, but oriented orthogonally and sandwich together. That was the first one. Well, then there is the old idea existing in, it still were bulk crystals. Bulk crystal means bulk, right? So basically what the bulk crystal? Bulk crystal is what grown up, and there is somewhere, there's optical axis there, right? You do the crystallographic analysis, X-rays, and you find out where the optical axis is, and then you kind of do the calculation of phase matching, and you find out that if my pump will go at like 29.5 degrees relative to optical axis, then I would have somewhere close to what I need. So you have to cut this piece out of the bulb of the crystal, perpendicular, because you want to go perpendicular with your pump, with laser, and so on, and that's what they do. Of course, the accuracy of cutting is not so great. You go there, but you still have to find a little bit, but nearby. Okay, and then you cannot do anything else, so that's all what you have. So that's what the bulk is about, and the normal phase matching. The only parameter you have a thickness. When changing the thickness, you can change the size of this sine x over x function, sinc function. It's broader spectrum or narrower spectrum of the algorithm. But then, there's a fact, it's called the periodic phase matching. It's really going back to 1962. Blomberg and his colleagues discovered that. Basically, what was the discovery? Discovery was, so for the phase matching, you need frequency and k-vector match, which means this is k-vector of the pump, this is signal library, they have to be exactly the same. What if you do that and there is a mismatch, gap? This one ends here, this one ends there. There is a gap. Can you somehow fill this gap with something? And the answer is yes. If you have a periodic process, electromagnetic wave might propagate into the periodic structure, what it does. Remember Bloch's equation, right? It's everywhere in physics, because lots of periodic structures, like even like regular crystal structure is always periodic, the crystal lattice is periodic, and so on. So you will come up with something Like remember, what is this Brillouin zone? What is on the vertical axis? It's energy, right? On the horizontal, there's k vector. So it gives you some k vector behavior, right? Associated with that. It comes from the solution of that differential equation. So if you can introduce some periodic function with the period, then you have k vector that is inversely proportional to the period, right? 2 pi over lambda is the number of the period of your modulation. So with nonlinear crystals, what you can do, you can take nonlinear crystal, and that's basically was the essence of the Blom-Darn's proposal. You alter the direction of the optical axis or polarization axis, by polarizability of the crystal, up and down, up and down, up and down. So if you do that with the period of lambda, you have this k, and you can do many more phase matchings than in the bulk. You really kind of, the whole kind of field becomes available. You can do all the interactions you want. Actually, you don't need to look for any new direction anymore. You just pick up your crystal, whereas the optical axis, and this is just in one, they just cut it perpendicular right here, and that's what it is. Yeah, of course, if you start to use this directly as a bulk, there will be no match whatsoever. But if you know how much is mismatch, you can always calculate the period that will eliminate this mismatch. And then you can do lots of interactions. These, for example, here it's a laser, 775, 532, 532, 415. This is polarization of the laser. And this is what the signal and either waves you can have. And this is what kind of period of modulation you have to accomplish for that. The one very interesting thing here is when you use the bulk material and natural dispersion of polarization inside the material, you always have to have at least one wave of different polarization than the two others. Because there are three: pump, signal, and either, right? So type 1 is, for example, pump vertical and both are horizontal. Or other way around, horizontal and both vertical. Type 2, pump vertical, and output is horizontal and vertical, right? The situation when they have all the same polarization is not available at all in bulk structure, just because of dispersion dependencies. Here you can do that. Extraordinary, 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 for example, 775 for 2 entangled photons in 1550 nanometers, and also when you go to the infrared, the periodicity is increasing. It makes it easier to ball, actually. So that's what you can do. And in fact, the other thing, sometimes it's O, and people call it type 0 phase matching. This would be type 2. This is, no, that's still the same thing. So type 2, type 1, and then it's a type 0, when you don't need to alter any polarization. And this type 0 has the highest nonlinear coefficient. So efficiency of conversion will be great. Well, how you do that? It's very simple. You have to pole it. Well, as you can see here, it says, at that time, it was like 500 microns, half a millimeter thickness. It's basically a flat surface. So you have to put mass of basically you have to define your places where you would like to have electric field applied, right here in the middle, and not applied. Right here it's a photoresist. Photoresist is dielectric. Why do we need that? Because you create a situation like this. You put your nonlinear crystal. Now, here, as you can see, is exposed to the electrolyte. Electrolyte is simply just conductor of electricity, bringing it to the surfaces here in a more uniform way. But then here it's protected, as you can see, this yellow thing, it's a photoresist, so the field is not applied. So original orientation is up. But now, when you apply about 20 kilovolts, very high voltage, to this. So what happens is this majority of nonlinear crystals, well, basically almost all nonlinear crystals, they are ionic crystals. Because only ionic crystals can create internal dipoles. Because when you have ions in the corners of your crystal lattice, there are dipoles. And these dipoles create a particular distortion in the electric field inside. Remember nonlinear crystal? You need distortion of linearity. That's where it happens in the crystal lattice. So there's always ions, and what it does, it just takes the ion of lithium in lithium niobate and pull it a little bit. And when you pull all of them, you distort the distribution of electromagnetic field so much that the optical axis basically flips in the opposite direction. So that's orientation of the Chi2 nonlinearity. And then it's enough to create the modulation of the phases. That's how it really happens. This is the current behavior. This is voltage. You see, then you increase, then you see they start flipping because current means the motion of charges, right? So they started, then you fix it, and then go back, and that's it. So that's what you have. And this, how to check it? Well, the interesting one, basically, you see, this is the basic phase modulation. It's very hard to see because it's still transparent subject. But it's interesting if you use the HF acid. It's etching very quickly every material, like even glass. It happens to be that it etches the speed of etch depends on the orientation of the optical axis. Basically, you can etch it for like 15-20 seconds and then wash it out, and you can see what is the periodicity of your structure is. So that's very interesting technical way of doing it. So what you can do? Well, now you can put it inside, periodically poled lithium niobate. You can put some laser and see what comes out of that. Well, there are several things. First of all, phase matching happens. Phase matching happens, but also phase matching happens of different types because it's still kind of, there's a main thing you calculated for the collinear case, but then there is still some degree of angles is available, but it's still like a quasi-bulk material. So you can have different interactions, different polarizations. For example, here, you see this picture of, this is a 532 nanometer pump, and this is the filter at 812 nanometers. It's visible, red, a really dark red. You see one ring, second ring. But if you put a polarizer, you will discover that polarization of this ring and this ring is opposite. So this belongs to E to EE, this one to E to OO interaction. So two different interactions, and basically you just observe that because you just put a camera here and camera just average over time. Well, so in addition to just different directions, what else is interesting and used to different phase matches is the fact that if you modulate any parameter using square function, it has some spectrum encoded to it. There are always harmonics exist. So in principle, you can use not only the main K vector, if you want, you can use this K vector, this K vector, this K vector, that, for any other phase matching structure. The only difference is the efficiency is going down. Basically, this is showing the different orders and how the efficiency, you see, like goes down, down, down when you go to a high number. But it's also could be useful when you start to engineer entanglement. This is showing you that, it's again like different interactions, and also, well, when you have the bulk material to change parameters of your entangled states, what you have to do, you have to tilt your crystal, so expose it to different phase matching conditions. When you have situations like this, you cannot tilt anything, you just is given to this thin layer periodical pole. However, what you have is extra parameters of temperature. The lithium niobate has extremely sensitive dispersion. When you look in the, usually dispersion is described by Solmeyer's formula for every material. And in lithium niobate, it even has a temperature included in those. So you can change, it's a really good parameter when you need to tune up a phase matching. You start changing temperature and you can change the size of those rings. Let's say I may have even, okay, this is just showing you like oops, different interactions. Okay, yeah, so just different interactions and different temperature can change. Okay, so what you can do with that, for example, you can have one infrared, one visible, one infrared photon, and you can measure the incidences between them. This is still correlated states. So instead of bulk material now, the one that we use with those two sets of rings, now we have this, and we can have visible here, infrared there, to measure coincidences between those signals. Here it is. It's just, it shows you, so this is like one interaction, this is the second interaction. Let me see. Now, it's all correlation. Photon here, photon there, photon here, photon there, correlation. But we want to have a superposition. The task is, can we design this type of state? It's a very interesting state. It's entangled in frequencies and polarizations. You see, in terms of polarizations, it's H, H, V, V. Extraordinary, extraordinary, ordinary, ordinary. But also, it's 8, 10, 15, 50, 8, 10, 15, 50. So it's basically H, V, V, H, but at two different spectral components. Why? Well, our motivation at that time was very simple. As you can see here, this is it's really for quantum cryptography, because to do this quantum cryptography over fiber, you need 1550 nanometers. That's what goes in the fiber. The second photon will be staying at Alice's side, where you send it from. So you don't need to bother to go in the fiber. Why you don't want to bother? Because the visible light detectors, silicon alloy photodiodes, are much, much better in terms of signal-to-noise ratio than the infrared detectors. So you want to have visible detection and infrared detection. This will go in the communication line to the ball. This will stay with Alice. But you want to have this polarization entanglement. How to make this? But because this is 810 and 1550. Before we did it all at the same wavelength. Can we design something like that? Okay? We need to satisfy two conditions. So polarizations, HHPV, and 810, 1550. So if you go to the tuning curves of harmonic down conversion, you can discover that this is 800, like 810 is something. For example, you see this is one interaction, this is second interaction. These curves are pairwise. This one, and this one, this one. But if you go to these places, right here and right here, or where it's 1550s, right here and right here, you see they completely overlap. Here and here, here and here. You cannot distinguish from which of these curves your photons are coming from. So that's what the theory tells you. Now you have to realize this in experiment. So how to realize this experiment? So you have to have two interactions, this E to OO and E to E, to overlap. It's two different interactions at two different spatial positions. So 810 is smaller column, this one is a bigger column. That's one thing, and you have to align them. This we can do, so alignment in terms of the space, you can do using temperature. You see, for example, at 120 degrees, it's a two distinct ones, and 100 degrees closer, 80 closer and 60, they just sewed their overlap, and now you don't see the difference between them. So temperature helps us to align spatially. But then, let me see if I have it here. No, okay. So spatially we align, spatially indistinguishable, polarization is there. Are there any other type of distinguishability indistinguishability exists? It's intensity. If one process is more intense than the other one, it is the coefficient in front of the terms, and it becomes this. So you really have to make sure that intensity of these two processes are also the same, and that becomes a little bit of a problem, because one of them is stronger, another one is weaker. What you can do? So the weaker one happens to be available at, you see this one, EOO. It's a type 1 parametric down converter. It's normally available here even without any polling. But the second one is EEE, only exists with the pole. So if you do 50-50 polling, normal 50-50, it will be maximal with the linear coefficient provided by this process, but it's too much. This one is much stronger than that one. Well, in optics, in engineering of quantum states, it's very important, very often, not only in distinguishability like in space, frequency, but also in intensity. It's an old principle. Many of you have done the optics experiments in the lab with interferometers, like Mark Zander or Michael's interferometer. If transmission of one arm of the interferometer is lower than the other one, what happens? The visibility goes down, right? The maximum visibility will be when the transmissions are equal of both arms. And opticians know that. There is an old trick. If you have an interferometer, and for example, one arm is more transparent than the other one, what do? You just put ND filter, neutral density filter, in the other arm to equalize that. The overall intensity goes down, but the visibility of the curve is getting better. That's a rule of interference. The same here. So we could reduce the intensity of the stronger process. How would you increase the intensity? Well, the trick is to pole it with, not with 50-50, but something like with 60-40 or 70-30 periodicity. When your period here is not 50-50, your efficiency of conversion is going down. It's like you're suppressing the efficiency. So you can do that and equalize this, and that's a result. As you can see, well, even in the frequency, it was a little bit of mismatch. It's kind of, magnitude is good, but frequency mismatch, it's from here, so it's a little, not, you can immediately see the violation of Bell's inequality will be not very maximal in this case, because there is a degree of distinguishability. Surely enough, when we did that, it was this curve right here. It's about 76%. It's enough to say this is in the quantum domain, but not very good violation of Bell's inequality. But in this structure that allows us to get the visible and infrared entanglement engineered together. So I try to show you the principles of first, how to engineer entanglement just by switching from bulk to periodically polling, and then how to use different aspects of periodically polling to move the frequency, space, and intensity to build up superposition, which means complete indistinguishability, and the correlation. And that's the two tools that you can use to generate entangled states. Okay. One more tool we have, remember the KVAC. the K-vector triangular has to be closed and so on. And what if, for example, we have the crystal here. Let's say in this direction we have a phase matching for some process, but we add polling in this direction. Well, polling automatically gives you K-vectors. But this K-vector will be added to your processes. So basically what it does, it duplicates the scattering geometry. So basically, well, look at this like, this picture is the same, just 90 degrees rotated. So basically you immediately duplicate this. Now you have special points where you don't know to which process it belongs to. You see, the polling could have a very interesting effect. This is just, so this is 830 nanometers, this is 730 nanometers, different frequencies. By the way, you see it's all black and white, simply because high sensitivity CCD cameras, they cannot have enough sensitivity to do color. Then you can ask why you have these nice concentric rings of colorful rings of type 2 down conversion that were taken back in 1994. The answer is very simple. They are not real. They're artificial. The pictures were done with exactly like this, with interference filters. You see, it's bandwidth, bandwidth, center bandwidth, center bandwidth. That's this what was taken at that time. Then they were overlapped. So you have like 4. At that time, actually, there were not even CCD cameras. They were regular films. You take one negative, one negative, one negative. You put them all 3 together. Anyone who played with photography, you know this trick. You put them then together, or for example, you have a photographic paper. You put one exposed, the second one exposed on the top, exposed on the top, and then you make process your photographic paper, and 3 of them are overlapping. And what you do after that, you take the color pens and you make it red, yellow, and blue. That was the nature of all those first rings. But the one ring I've shown you at some point was for the type 1 down conversion, and I still have it even on my website. It's a real one. Why? Because to make it visible, you really have to go away from quantum domain into classical by simply cranking up the power of your laser. You increase the power of your laser, your device goes from spontaneous regime, from real parametric amplifier, and then you can put CCD camera and you start to see the colors, basically. So it's nice for demonstration, but it's not quantum at all. Anyway, so again, visualization in quantum is hard. Really. Anyway, so as I said, so periodicity can help. If you do periodicity in 2 dimensions, you really can design very interesting structures of phase matching, and it's a great tool to have indistinguishability in 2 dimensions. That's yeah, something like that, as you can see here. So if you have the interaction that I told you about, 810, 1550, then and you multiply it using multiple things, and you see how many different, like this spot here, you don't know it's this one, it's that one, and if you go to here, so you also don't know lots of possibilities to design indistinguishability between different processes. Okay, the last thing, again, we keep building the toolbox of designing entanglement. Okay, so as you can see, that was the picture we discussed before. So nonlinear crystal, this is just a dichroic mirror, removes the pump, because you know the pump is millions of times stronger than down conversion. The efficiency of down conversion is directly proportional to the nonlinear coefficient. And nonlinear coefficient is 10 to the minus 9, 10 to the minus 8. If you integrate over all volume of the crystal, it becomes like 10 to the minus 7. So you have to put 10 million photons to get one photon out of down converting. So you really need to remove it all in order to see this picture, as I told you. Again, here it's also artificial colors. So this is 2 arms, and I told you you can send one to Bob's, one to Alice, and so on, polarization entangled state. If you look from the top, that's what it is. Try to align it in the lab, you will discover it's a pain. That's really why Anton Sergienko at that time asked me to come to show them how to do that, because it was very painful. We came from that pain earlier than they did, so it was easier just to put crystal and all my stuff in the pocket and do it even there. Actually, at the end, it was fast. In 3 days, we did that experiment. So I spent 3 days there, and after that, Paul Kriat wrote a paper, finished this, and I was really interested in, when you know what you're doing, you can do it very quickly, but it was really painful. You have to down converter crystal, find these 2 directions, put these 2 detectors. I remember it's single photons, you cannot see them. It's all like you're fishing in the dark, basically. There are lots of tricks how to help this, but it's still a lot of pain. So, would it help to have this, for example, one single direction? When both polarization go in a single direction, well, that's great. It's possible. We'll just tilt it a little bit away from the condition. So when they just top ring and bottom ring just touch each other, and now there's one single point of indistinguishability, not 2 points, one single point of indistinguishability. And this one is just, but it's not entangled. It's correlated. There is no second option, right? There's only one beam. It's HVVA, but they are together in one single beam. So we have correlation, we need to arrange for superposition, and thanks God, in optics is easy. Superposition is done with beam splitting. Again, our Hadamard transformation. Beam splitter, you put it here, boom, boom. What happens to that? Well, the photons are photons. They come together to the beam splitter. They have to go, they have 4 probabilities. One here, one there, HV, or VH, or 2 of them can go here, nothing there, or vice versa, because beam splitter, it's a piece of glass, right? You put 2 photons, and it splits it in 4 probabilities, 4 options. That's it. It's a classical state. You put in the product state, you end up with product state. It's factorizable. However, if you take it to one detector and second detector and start to do coincidences means that's what, again, we come into the fact you have to bring these 2 signals together to evaluate the joint probability. Sometimes people call it conditional probability, it doesn't matter. So one particle on conditional on the other one, it has to be done here, and here we are. When 2 photons goes in one arm and 0 in the other, you're gay. Remember I told you, if you have 0, you don't measure it. Because 0 doesn't give you a click of the detector, so you don't see this. And vice versa here. So these 2 terms are not present in what your system tells you as an observer. If you don't see it as an observer, it's like it's not there. It's a trick, of course. Of course, it's a trick, it's an engineering trick. The result is that when you measure this, it will be HV minus VH, as if it was that original entangled state with those 2 rings overlapping, but with much more simple configuration. In fact, what you can, so if this is crystal, if this is delay line, basically this delay line is just takes the horizontal and vertical and delay them like this. It's a birefringent delay line. So when they are perfectly overlapped, you have this, and you are right here at the bottom of this dip. If you make them a little bit more distinguishable, then they go right here. So this is like polarization analog counterpart of Hongo-Mendel experiment that we'll be talking about later, next lectures. Okay, so effect to observer is the same as if you would be sent the genuine entangled state, but it's artificially made. You need to satisfy this condition, so these two detectors and coincidences have to be executed. So I would like to stress this, that in principle all these entangled states manipulation used everywhere is divided into these two categories. I call one of them is a genuine entanglement. It's like the one from these two rings overlapping. So basically you can send it to anyone and say, here's, I'm sending you entanglement in polarization. They just have to do a set of measurements and verify that this is entanglement. This one, I would call it, would be called operational entanglement, which means you have to provide also instructions how to observe that. Because your observation have to be conditioned on the particular structure, procedure of measurements. But if you do that, your outcome will be exactly the same as the other one. So how, what's underneath of this, what is under the kind of hood of this engine? The elimination of unwanted amplitudes in quantum states during the observation process. That's why you eliminate them by non-observing. Or another physical term is filtering. In principle, filtering has been used a lot in quantum optics to engineer entanglement. To some extent, you can trace it back to, like, what is the last classical state, the more like nearest to the quantum domain, is a coherent state, right? It's a state with equal distribution of everything there. So you take two coherent states, multiply them, it's a product state. How to get, for example, the entanglement out of that? So you have to break somehow symmetry. You have to filter out some components. Because here, you see, these four terms highlight the symmetry of the operation of the beam splitter. You put the state, and that's naturally what can come out, what comes from the electromagnetic theory of scattering on the glass, basically. But when you eliminate some component of that, the outcome observable becomes non-factorable, because you eliminated a portion of that. It's like you have two products, A plus B and A plus B, right? Product. Then multiply that. There would be four terms, right? If you take two terms away, it becomes non-factorizable. That's a trick? Yes. That's an engineering trick. And that's why it's operational. But the outcome is exactly the same. And very often, the operation of the system is much more reliable, stable, and easier to align than the other one. So that's kind of how it came about, basically. And what you can do some measurements with these systems, just as I told you. So it's the distinguishability between these two photons gives you position of this dip, but then if you throw inside a sample, then this sample, if it's birefringent, it just moves the whole thing, and you can measure how much it got moved, so you can measure the degree of birefringence of this material, for example. It becomes a sensor. We have a whole lecture on sensors later on. Let me just last thing. Role of detectors. So what we did the source consideration, how to modify the source to get different entangled states. How to modify propagation, like beam splitter and coincidence detection, structure of the propagation leading to particular events. Role of the detectors. So if you have laser and attenuate the laser, it becomes Poisson. Laser is Poisson, this is attenuated Poisson at the single photon level. Poisson. when you have correlated two photon states, as I showed you, you detect one of them with like avalanche photodiode. Whenever you have a click, you can open the gate and close it. So you send it through. You eliminated zeros, but you did not eliminate when, for example, 2 and 2 goes, 3 or 3 goes. You cannot distinguish them because avalanche photodiode is not sensitive to that. The most advanced device would be photon number resolving device. You can go, it goes here and it has 0, 1, and 2. It can tell you, was it nothing, 1, 2, 3, 4, whatever. And you can pick up and open the gate only when the desired outcome is detected here. So you can have heralded source of 1, 2, 3, and so on. And one of the detectors that can do that is the transition edge sensor. It's a superconducting detector. There are two types of superconducting detectors these days. It's a transition edge sensor, it came first, but then there is also nanowire detector. It's a separate topic. I'm not going to cover this, but if someone is interested, we can discuss it. So basically, what is the transition edge sensor? It's a piece of tungsten at an extremely low temperature, 50 millikelvin. So it's so a low temperature that appearance of one of the photon, absorption of the photon changes the conductivity, but still not throwing you out of the superconducting regime. So you are on the sensitivity curve. So it's like a thermometer with resistivity of this to be proportional to the energy deposited to this. Well, as with very thermometer, after the detection event, like after you measure your temperature, what do you need to do? You have to get it back to zero, right? And this process is a little bit lengthy. That's why those devices are slower than many others, but they are really can distinguish different number of photons. And when we did it originally with John Martinis, the guy who later moved into the quantum computing business, but he was in superconducting domain at that time. To demonstrate this, it's basically, this is in my lab, this is the whole cryostat. They designed an excellent cryostat. Basically right here you have 50 millikelvin inside. We were thinking how to illustrate that with, Hong-Mandel effect. Two correlated photons goes to the beam splitter, and either 2 goes here or 2 goes there, right? So, and the fact, how do people claim that 2 goes here, 2 goes there? By the fact that there is no coincidence, right? 2 goes here, nothing there, or vice versa. There is nothing to detect with the second detector, so you will never create enough. You will never create 2 pulses to coincide. Now we put them here, one there. Now we can detect singles and doubles. Singles goes to coincidence circuits, and doubles are detected independently. And this is just a polarization version of the Hong-Mandel interferometer. You just, instead of 2 arms, you have 1 arm but 2 polarizations, basically. And you see, this is the coincidence rate for singles. But whenever you have deep in singles, you have 2 peaks for doubles. And if you consider everything, then that's what it looks like. So this is the blue, it's 1, 1. 1 goes to one detector, 1 goes to, this is conventional Hong-Mandel, but it's accompanied at the same time with 2, 0, 0, 2. And if you add the probabilities of this and this, it will be exactly the probability of that. So basically, it's nothing else than direct observation of those 2 other terms that I canceled in the previous slide. Remember the 2002, but photon number resolving detector allows you to detect this. What it also allows you, really, it allows you to do more, to do operational, like post-processing entanglement out of any source that has correlation. Basically, with this, I was, it's N. That's where we realized that if you want to get entanglement, I can get it from the light bar, basically. What comes from the light bar? It's a thermal radiation, right? It has a correlation inside it, right? Yeah? What I do? I attenuate it to kind of single photon level. It becomes basically Poisson. Poisson, what the Poisson is, the probability of having 1 photon, 2 photon, 3 photon, 4 photon. It's P of 1, P of 2, P of 3, right? It's a distribution, depending on the intensity. Okay, I put the beam splitter, I split it in tolerance, and I put these detectors that will give me, will detect only the one here and one here. So original P of 2, but I will not see anything else. I only see the P of 1 and P of 1 that is coming from the P of 2. And I eliminate all other terms. And that's it. The detection of the coincidences will tell me what the intended state. Why? Because on purpose, I already had correlation originally. The only thing is, why thermal radiation cannot give you the same Bell's inequality violation? Because you have Poisson. Poisson has what you want and many other terms, but you don't want. This many other terms gives you background. If you remove this background by post-selection, you can detect this particular number of photons, then you can remove that. You can generate something that would look like entanglement operationally. You can use it, but with particular instructions how to operate this. So these days, entanglement out of the mysterious feature becomes a really kind of optical engineering. And many other sources of entanglement. I talk about the nonlinear optics, but many of you have heard about the large domain. It's called the quantum dots. For many, many years, people trying to design the photon gun. Because in principle, what you need to have two correlated photons, right? If you have two photon guns that emit photons on demand, and they are absolutely indistinguishable, then you put them on the beam splitter, you have what you want. But the problem is to make them absolutely indistinguishable from quantum dots. That's the biggest problem the quantum dot community is struggling for many years, and that's another story. But I hope I gave you enough flavor towards understanding that you can engineer it. The main guidance is superposition and correlation, and tools to create superposition, propagate superposition, and detect. And filtering or post-processing is also a valid tool, but you have to carefully document what you do. Because for the application, for practicality, it doesn't matter whether you have genuine entanglement or you have instrumental entanglement, basically. Okay, that's all for this section. Thank you.